Hello and welcome back to the second part of this lecture on gauge invariance. In the previous part we had discussed the inconsistency in Ampere's law and Maxwell's corrections to it, and the notion of the scalar and vector potential fields, and how we could compress the four Maxwell's equations into two inhomogeneous second order differential equations involving only the scalar and the vector potentials. So in this part we will look at what is known as gauge transformations. Now how did we reach this gauge transformations? This is where we had stopped in the previous lecture. So this was these two equations, like we said, it contains here we had it contains the two potentials. One is a scalar potential, another one is a vector potential. The notion of these two potentials comes to us from the two homogeneous Maxwell's equations, and using the inhomogeneous Maxwell's equations we were able to obtain these two equations. That means all the information in the Maxwell's equations is contained within these two equations 8 and 9. Now how did we obtain this, and how to simplify this and write it in a more elegant form? To know that, you can just have a look at the first part of this particular lecture. Now if you look at these two equations, they are first of all they are second order differential equations. So the boundary conditions, number of boundary conditions will remain the same here. And next thing is that we notice here is that they are still coupled. So if they are coupled, we would like to uncouple them and obtain two differential equations, one in phi and another equation in A. So how do we do that? We do that by exploiting the arbitrariness of these two potentials, and this is what is known as a gauge transformation. So the idea here is basically this. We have to keep in mind that it's only the electric and magnetic fields which are the real fields. Okay, they are the ones which produce real physical effects. This is one thing that we should not lose sight of. I mean, we are introducing these new potentials phi and A, but this phi and A, they're actually mathematical constructs which we introduce in order to simplify the problem, or in order to solve the problem in a much more convenient manner. But this phi and A, they are not real physical quantities. The real physical quantities are going to be the fields, that is electric and magnetic fields. So this means that as long as your electric and magnetic fields remain the same, you could have you could choose any set of phi and A, as long as this electric and magnetic fields remain the same. So for instance, if I have two sets of potentials, this is the first set phi and A, and this is another set phi prime A prime, and if it happens that this phi A, it gives us electric and magnetic fields C and B, phi prime A prime, it also gives us the same electric and magnetic fields E and B, then both phi A and phi prime A prime, both of them are equally acceptable in that particular problem. Okay, and we will obviously choose the one which is simpler, which is going to make our problem simpler to solve, easier to understand. So this is the basic idea behind gauge transformation. So basically what we do is any transformation of the potentials, that is from phi to phi prime or vice versa, or A and A to A prime and vice versa, any such transformation between two sets of potentials which leaves the electric and magnetic fields unchanged, these kind of transformations between potentials are known as gauge transformations. And because in case of gauge transformations, the electric and magnetic fields, they remain unchanged or they remain invariant, we say that the electric and magnetic fields are gauge invariant. Okay, so any gauge transformations do not affect the electric and magnetic fields, and hence they are known as gauge invariant. Okay, so now let's say originally we had this set of potentials phi and A. Okay, now I go from phi A, I go to a new set of potentials phi prime and A prime. How do I go? What I do is I take the original vector potential A and I add to it another vector field A prime alpha, and that will give us A prime. Similarly, I take the original scalar potential, and to that I add another scalar potential beta, that will, let's say, it gives us phi prime. Now since the electric and magnetic fields are invariant, that means whether you apply these potentials or you apply these potentials, the fields must be same. So for instance, if you take the magnetic field, okay, how do you get magnetic field? We get magnetic field by taking the curl of the vector potential. So whether you take the curl of A prime or you take the curl of A, in both cases the magnetic field must be the same. So it means curl of A prime must be equal to curl of A. This is the requirement for the gauge transformation. Now what you do is you just substitute here, okay, A prime, you write it as A plus alpha, okay. So curl of A plus alpha must be equal to curl of A. Now distribute this, curl of A plus curl of alpha must be equal to curl of A. So curl of A will get cancelled from both sides. So what is left behind is curl of alpha, which is equal to 0. We call this as equation number 1. Now if you look at equation number 1, what does it tell? It tells us that the curl of this vector field is 0. If the curl of a vector field is 0, it means that vector field can be written as the gradient of some scalar. Okay, so let's say we have a scalar lambda prime, then we can such that this gradient of lambda prime is equal to alpha. So this will ensure that the curl of alpha is always 0, because alpha is equal to gradient of lambda prime, and curl of alpha is nothing but curl of gradient of lambda, and curl of gradient of any vector scalar field will always be 0. So this choice of alpha is going to ensure that this condition number 1 is always satisfied. Again, in a similar way, if you look at the electric field, okay, the electric field will be same no matter whether you consider whether you use this set of potentials or you use this set of potentials. So okay, this minus grad phi prime minus dou A prime by dou t must be equal to minus grad phi minus dou A by dou t. This again is the requirement for the gauge transformation to be valid. So now we substitute phi prime is phi plus beta and A prime is A plus alpha. Okay, so phi prime will get cancelled, gradient phi prime will get cancelled, and dou A by dou t will get cancelled. So this will give us gradient of beta plus dou alpha by dou t, which is equal to 0. Now previously when we studied when we applied the gauge transformation condition on the magnetic field, we already obtained what is alpha. Alpha was equal to gradient of lambda prime, right? Alpha was equal to gradient of lambda prime. Okay, so we just substitute over here, and this gives us gradient of beta plus dou by dou t, gradient of lambda prime is equal to 0. Again, this is a time derivative, this is a space derivative. We can swap them around. I'll take the gradient outside, then I take the gradient operator common here, and I get gradient of beta plus dou lambda prime by dou t is equal to 0. So we call this as equation number 3. Okay, so gradient of beta plus dou lambda prime by dou t, this is equal to 0. So what does equation number 3, what does it tell us? It tells us that the space derivative of this quantity is 0. Okay, because gradient is a space derivative, so space derivative of this quantity is 0. So if space derivative of this quantity is 0, that means this quantity inside the bracket is independent of space. That means this quantity inside the bracket, it depends only on time. Okay, so say this quantity inside the bracket, that is beta plus dou lambda prime by dou t, we call it as it is equal to some function of time, that is k of t. So from here beta is equal to minus dou lambda prime by dou t plus k of t. Call this equation number 4. So we will now define new lambda. Okay, that new lambda is defined as the original lambda, which was lambda prime, minus the integration of this k from 0 to t. Okay, so I have just used a dummy variable here, tau. Okay, the tau takes the same range of values as t. Okay, so we just basically integrate this k, and that integral we subtract from the original lambda prime, that is our new lambda. Okay, so this is our new lambda that we have chosen here. Okay, so from equation number 5, what will happen if I differentiate this with respect to time? Dou lambda by dou t is equal to dou lambda prime by dou t minus dou by dou t of this quantity. Now you see that k is a function which depends only on time, right? So if k is a function which depends only on time, I have integrated this k, and then I am trying to differentiate this with respect to t. We are integrating with respect to time and differentiating with respect to time. Integration, differentiation, they are inverse operations of each other. So this will give us back the original function, which is k of t. So dou lambda by dou t is equal to dou lambda prime by dou t minus k of t. We'll call this as equation number 6. Now let's take the gradient over here. Okay, so gradient of lambda is equal to gradient of lambda prime minus gradient of this quantity. Now we already saw that this k is dependent only on t. That means this quantity will be because I have integrated with respect to time, so this will depend solely on time t. Okay, so if this depends on time t and you are taking the gradient of a quantity which depends only on time, then that means this quantity will be 0. So as a result, gradient of lambda will be equal to gradient of lambda prime. So with this choice of lambda, the gradient will remain the same. Okay, and if the gradient remains the same, that means alpha will also be the same. Okay, why should alpha be same? Because of this, alpha is equal to gradient of lambda prime, and here we have shown that gradient of lambda prime is equal to gradient of lambda. So whether you choose the original lambda prime or you choose this lambda, in both the cases we will get the same value of alpha. And if you get the same value of alpha, then we should get the same value of b, because what is a prime? A prime is equal to a plus alpha, and in both the cases the magnetic field is b. So choosing lambda or choosing lambda prime, either of them will give us the same magnetic field b. Okay, so this was our equation number 2 and 4. Okay, and this was with the choice of this new lambda. Okay, this was the time derivative of lambda, and this was the gradient of this lambda. So now from these two equations, from equations 2 and 7, comparing equations 2 and 7, we say that alpha is equal to gradient of lambda. And comparing equation number 6 and 4, okay, comparing these two equations. Okay, so here we have dou lambda prime by dou t minus dou lambda prime by dou t plus k of t, and here we have plus dou lambda prime by dou t minus k of t. That means this entire quantity on this side will be equal to minus dou lambda by dou t. So beta is equal to minus dou lambda by dou t. And what is alpha and beta? Alpha and beta was the original changes, okay, that we had made here. This was alpha and this was beta. The original set of potentials we just added to the vector potential, we added alpha, and to the scalar potential we added beta, and we got the new potentials. And we found out that in this cases the gauge transformations to be valid, the value of alpha and the value of beta, that's what we got in terms of some function lambda. Okay, so a is this and a prime is this and phi prime is this. So if I choose a suitable lambda, then the following is a gauge transformation. All you have to do is this alpha, I just substitute over here that a prime is equal to a plus gradient lambda, and phi prime is equal to phi minus dou lambda by dou t. So here this lambda is known as a gauge function. So essentially what does this mean? What does this mean? It basically means this, that the electric and magnetic fields will remain unchanged when I add a gradient of some lambda to the vector potential, and simultaneously I subtract dou lambda by dou t to the scalar potential. Okay, if I do that, then the electric and magnetic fields will remain unchanged, and the new set of potentials that we got, that potential will be, we say that it has it's a gauge transformation from the old set of potentials a phi. Okay, so now we come to a specific type of gauge which is known as a Coulomb gauge. Okay, this Coulomb gauge is also known as radiation gauge, or is also known as a transverse gauge. Okay, we'll see why it is called that in a short while. Okay, so in Coulomb gauge, what do we do? So everything, it depends on this. Okay, what kind of the gauge transformation? What is the parameter that governs the gauge transformation? The parameter is lambda. So everything depends on choosing the lambda wisely. Okay, so a particular specific choice of lambda will give us what is known as a Coulomb gauge. A specific choice of lambda will give us what is known as a Lorentz gauge. These are two different gauges that we'll be studying now. So we choose this lambda, okay, this gauge function lambda, we choose in such a way that the divergence of the new vector potential is 0. Okay, choose lambda in such a way that the divergence of the vector potential is 0. So if divergence of vector potential, that is a prime, is 0, a prime is nothing but a plus gradient of lambda. Okay, so divergence of a plus divergence of gradient of lambda must be 0. Now divergence of a, and what is divergence of gradient? It is nothing but the Laplacian. So divergence of a plus the Laplacian of lambda is equal to 0. So from here we get the Laplacian of lambda must be equal to minus the divergence of a. So call this as equation number 1. This equation number 1 gives us the condition for lambda on the Coulomb gauge. So if I am given a particular set of potentials, okay, so all I have to do to know what value of what is the gauge function, all I need to do is just take the divergence of A, okay, and put a minus sign in front, okay, that will be the Laplacian of lambda, and then solve for lambda, okay. Then solving that lambda, that will give us the gauge function, and then you find the gradient of lambda, then you find the time derivative of lambda, add them to the A and the phi, and that will give us the new set of potentials. So equation number 1 is the key in the Coulomb gauge. So in that case, the inhomogeneous equations, what do they become? Okay, so here I have written for ready reference, this is where our inhomogeneous second order differential equations. So what have we chosen? In Coulomb gauge, we have chosen lambda to such that divergence of A is 0. So this term is going to become 0 in the first equation, and in the A equation, this term is going to be 0. So here we had on the left hand side two terms. So from two terms, one term has vanished. So this is going to depend only on phi. So we have uncoupled this. In the second equation, okay, so we had a A here and a A here, and then in this term we had a phi and a A here, okay. So this will vanish, but still there is still a phi here. We will have to do something about this phi, which we will see in a short while, okay. Now this is going to vanish. So as a result, from the 4 terms, we will have 3 terms on the left hand side of the second equation, okay. So the first inhomogeneous equation will become this, and the second inhomogeneous equation will become this. I have just taken this dou phi by dou t term from left hand side, I have taken it to the right hand side. Now as you can see here, equation number 2, it is completely uncoupled, so that is fine, and we can easily solve this because this is nothing but the Poisson equation. But equation number 3, it is not uncoupled yet, right? So we will need to do something about this one. Okay, equation number 2, it is just a Poisson's equation, and we already know what the solution of this one. The solution, this general solution, is 1 by 4 pi epsilon naught, okay, integration of rho by r minus r prime integrated over the tau prime volume, okay. So this is the instantaneous Coulomb electrostatic potential, and this is the reason why it is actually called a Coulomb gauge, okay. This is the reason. The next equation, equation number 3, okay, over here the divergence of A term has also vanished here, so and we have this. Now please note down this last term on the right hand side, the second term on the right hand side of equation number 3. This second term on the right hand side of this equation number 3 is irrotational, okay. Why is it irrotational? Because it features a gradient. Now if you think about it, this term, it says basically that this term is a gradient of something, okay. Now we already know if the curl of some quantity is 0, then that quantity can be written as the gradient of some other quantity, right? So here we are writing, just turn it around now. Here we are writing this as the gradient of some quantity. So if this is the gradient of some quantity, then I mean this is a scalar field. This gradient, taking the gradient, this will give me a vector field. Then this resultant vector field is basically a gradient of a scalar field. That means that this entire vector field that we have here, okay, the gradient which when it applies on this, we get a vector field. That vector field should have a 0 curl, okay, because it is only when the curl of a vector field is 0 can we write it as a gradient of a scalar field. So since we have a gradient here, that means this quantity can be written as the curl of some this quantity can be written as some vector field such that that vector field has got 0 curl, and if a vector field has got 0 curl, then we call it as a irrotational vector field. So this means this term on this last term on the right hand side of equation number 3, this term is an irrotational, contains an irrotational quantity, okay. Now if you look at dimensional wise, okay, this first term has got dimensions of mu naught current density. That means this term also should have dimensions of mu naught current density, but of course that current density will be a irrotational current density. So it suggests, so one suggestion that we can make here is perhaps this irrotational current density will get cancelled by some irrotational current density which comes out of this J here, okay. So this is one suggestion that we can have. So let's try to explore this suggestion and see if it really works or not. So for that, we'll just clarify about what is this irrotational and solenoidal fields that we're talking about. This is what an irrotational field looks like. So when I say irrotational current, we also mean longitudinal current. That means suppose I have a point. From this point, the current, it radiates outwards, or maybe the current radiates into a particular point. So if the current is such that it radiates from a point or radiates into a point, then that current is known as a irrotational, or it is known as a longitudinal current. So we'll just call it as JL. Okay. So now you can see immediately from here that because this is irrotational, that means its curl will be 0. Its curl will be 0, but its divergence, it's diverging out from a point. Its divergence will not be 0. That means divergence of this JL will be non-zero, and since it has got 0 curl, therefore curl of JL will also be 0 in this case. So this is what happens in case of a irrotational current. The curl of the irrotational current will be 0, but the divergence will be non-zero. Now what about the other type? The other type of current could be what is known as a solenoidal current. Solenoid, it comes from solenoids, where the wire, it just loops around an axis. So if the current, it loops around an axis which passes through our reference point, then that is that field is a solenoidal field. And here if it happens, if it's a current, then we call it as a solenoidal current. And because the solenoidal current, it is also tangential to the radial vector. Here it is along the radial vector, so that's why it's longitudinal. Here at this point, let's say it is perpendicular or tangential to the radial vector, so that's why it's also known as a tangential current, JT. And you can see here, because this vector field, it curls around this point, so the curl of this JT will be non-zero, but it does not diverge out, so the divergence will be 0. So it will just get reversed here. The divergence of JT will be 0, okay, unlike this case, and the curl of JT will be non-zero, unlike this case. Okay, now why are we referring to this? We are referring to this because at a point, suppose this is the total current J. Okay, at a particular point, let's say this is the total current J. This total current, I can always break it down into a longitudinal component and a tangential component, right? Because JL and JT. So J will be equal to JL. J is equal to JL plus JT. So total current at any point will be a combination of an irrotational current as well as a solenoidal current. So this is one thing that we need to remember. So what we need to remember is curl of JL is 0, divergence of JT is 0, and J is equal to JL plus JT. Okay, where JL is the longitudinal current or the irrotational current, and JT is the solenoidal current or the tangential current. Okay, so now coming back to this. Okay, so here we have this J. This J can be written in terms of J and JL and JT. So J is equal to JL plus JT. So now let's subject this J to the double curl. Okay, so curl of J. Curl of any vector's field is grad div of that vector field minus the Laplacian of the vector field. So curl of J is equal to gradient divergence of J minus the Laplacian of J. Okay, so this is the fundamental result that we are just using from here. Now we'll take this Laplacian of J and bring it on the other side, minus Laplacian of J, then this will go here, so this will remain as it is, and this goes on this side, and we'll get a minus sign here. Okay, so now what is J? J is, as we have seen, J is equal to JL plus JT. So J is equal to JL plus JT, and then here we have curl of J minus grad div of J. Now curl of J will be equal to curl of JT. Why is that so? Because what is J? J is equal to JL plus JT, and we saw that curl of JL is 0. So curl of J is equal to curl of JL plus curl of JT. Okay, so that means curl of JL is 0. So that means this will give us only curl of JT. In the same way, J is equal to JL plus JT, so which will give us divergence of JL plus divergence of JT. Divergence of JT is, as we have seen in the previous slide, it is 0. So this will be nothing but divergence of JL. So this we call as equation number 4. Now we can see here, compare the left hand side and the right hand side. Left hand side, this is a tangential, or this is a solenoidal component, and this is a longitudinal or a irrotational component. So this is a solenoidal component, and this is a irrotational component. This is a solenoidal component, this is a irrotational component. which means I could just associate these corresponding components. That means this component is equal to this, okay, minus Laplacian of jt must be equal to curl of j, and minus Laplacian of jl must be equal to minus gradient divergence of j. So this must be equal to this, and this must be equal to this. I'm just associating the corresponding components here. So Laplacian of jt is equal to minus curl of j, and Laplacian of jl is equal to gradient divergence of j. Call this equations 5 and 6. So equations 5 and 6, now they look very familiar because they are nothing but the Poisson's equations, right? Poisson's equation, what does it say in general? Okay, this is what a Poisson equation looks like. There is the Laplacian of some function f, if it is equal to k, okay, then we can easily find out the general solution of this one. What is the general solution of f? It is simply equal to minus 1 by 4 pi integration of k divided by r minus r prime, where the integration is taken over the primed position coordinate. Okay, so this is in general. So all you can do is you just need to apply this formula in equations 5 and 6. This is your f, and this entire quantity, this is k. Similarly, this is f here and this is k, and when you apply this, you will get the solution of 5, which is jt, this one, and the solution of 6, which is jl. So jt is this and jl is this. So this is equations 7 and 8. Okay, so this is equation number 3. So here again, going back to equation number 3, okay, right hand side, okay, we were saying that this is probably an irrotational quantity. This is an irrotational, not probably, it is an irrotational quantity because it features the gradient of some scalar field. Gradient of scalar field can be used for a vector field if that vector field is irrotational. So this is an irrotational quantity, okay. And then we saw that j can be written as jl plus jt. So now this phi, we have already found out the solution, right? From the first thing, it has already been uncoupled, and we know what is the, because it is just a Poisson equation, and we found out what is the solution of phi. This is the solution of phi, this we already know. So now we will consider the second term on the right hand side of equation number 3. So this is the second term. So all we need to do is this phi that we have here, we'll just take it and substitute here. Okay, just take this phi and just substitute this integral. That's how we got this 1 by 4 pi epsilon naught. Then gradient integration dou by dou t. I can take the dou by dou t inside. Okay, so we get rho by r minus r prime d tau prime. Okay, so now this dou by dou t, okay, when it applies on this, it will apply only on rho, because rho is the quantity which only depends on time t. 1 by r minus r modulus r minus r prime does not depend on time t. So dou by dou t does not apply on this, it will apply only on rho. Okay, so dou rho by dou t, and this we can easily identify using the continuity equation, because dou rho by dou t is minus divergence of j by continuity equation. So minus divergence of j will replace this one. So now we take the mu naught outside and then just rearrange this, and we get this quantity, and we can easily identify this because you see the quantity inside the bracket, that is nothing but the longitudinal current density JL. Okay, so here we got this quantity is nothing but mu naught times JL. Okay, so this was equation number 3. So J is equal to JL plus JT, and this equation is this term is nothing but mu naught JL. So therefore in equation number 3 we have mu naught jt minus, okay, this j I have just split into jt and jl, and then this is nothing but mu naught jl. So these two will get cancelled out, and as a result we will have only the solenoidal current which will remain on the right hand side of this equation. Now you see, now this has got finally uncoupled. The phi equation was already uncoupled, but the a equation was not. But by doing this analysis, we were able to uncouple the second equation also. Now it is nicely uncoupled here. And also one more thing that you notice here on the right hand side, it has got only jt. And what is jt? Jt is transverse current. Jt is transverse current. That's why this is also known as the transverse gauge. Okay, so it is called Coulomb gauge because phi has the form of the instantaneous Coulomb potential. It is called transverse gauge because A has on the right hand side of A, the transverse current comes into the picture, and it is called radiation gauge because the transverse radiation fields are given by A alone, because phi gives us the near fields. Okay, so this is the Coulomb gauge. Okay, so this equation number, we are already got this, and now we got this. So these two uncouple the inhomogeneous equations using the Coulomb gauge. Now we'll go to the next gauge, which is known as the Lorentz gauge. Okay, so in Lorentz gauge, what do we do? Okay, we again we'll have to pick the gauge function lambda. So in Lorentz gauge, we choose the gauge function in such a way that the divergence of A, in this case, it is not 0, but it is minus 1 by c square dou phi prime by dou t. So this we bring on this side. So if the divergence of A plus 1 by c square dou phi prime by dou t is equal to 0, then this is known as the Lorentz condition. So when the Lorentz condition is satisfied, then we said that those functions are known as that particular set of potentials are said to satisfy are said to undergo the Lorentz gauge transformation. Okay, so A is equal to A plus gradient lambda, and phi is equal to phi minus dou lambda by dou t. You just substitute. These are straightforward because this is the general prescription for finding the transformation, and we can easily identify here that if I take this, okay, so divergence of gradient of lambda, that will give us the Laplacian of lambda, and then here we have 1 by c square dou, and when we apply this 1 by c square dou square by dou t square lambda. So on this side, from here, from the first term we get Laplacian of lambda, second term we get minus 1 by c square dou square t lambda by dou t square, which is nothing but the D'Alembert operator. So the D'Alembert operator, it operates on lambda. And the other things, that is divergence of A plus 1 by c square dou phi by dou t, which is nothing but your L, to bring it this side. So the condition, okay, for lambda, that lambda must satisfy for the Lorentz gauge, this is a condition, the D'Alembert of lambda must be equal to minus L. So all you need to do is given whatever potentials are given, take the potentials and find out the L quantity, the quantity L, by divergence of A plus 1 by c square dou phi by dou t. Using that, you find out what is L. The negative of that L will give us the D'Alembert of lambda. Then solve the D'Alembert equation, and then you find out what is lambda. So that will give us the gauge function for the Lorentz gauge. Then the inhomogeneous equations, what will happen to the inhomogeneous equations? Here what happens? This quantity is 0, and because this is 0, what will happen is this quantity will vanish. So as a result, left hand side, nothing will happen to this equation. Okay, this equation remain as it is. This equation will have this two terms on the left hand side. So as a result, the inhomogeneous equations will become something like this. Okay, now it looks very symmetric now. Okay, these two here also we have a Laplacian, here second order time derivative, here also Laplacian and second order time derivative. So we could of course simply write this as, this is nothing but the D'Alembert of phi, and this is nothing but the D'Alembert of A. Okay, so you can see here it places both phi and A on equal footing. Okay, phi and A, they are treated equivalently, and because it involves the D'Alembert operator, like I mentioned some time back in the previous lecture, the D'Alembert, it ensures that the equation is independent of the coordinate system. So it becomes it remains independent of the coordinate system, and as a result of that, this can easily fit into relativistic considerations, where we need to create what are known as 4 vectors, 3 space coordinates and 1 time coordinate into 4 vector. So in that case, the Lorentz gauge fits in very beautifully. In the time static case, of course, the D'Alembert operator, it reduces to the ordinary Laplacian. Okay, and as a result, we'll just get back these two equations, which we can observe they are nothing but the Poisson's equations, and they have these solutions. And there's a special case of the Lorentz gauge which is known as the restricted gauge transformation. Okay, basically what we have is the set of gauge transformations, that is A going to A plus gradient lambda and phi going from phi minus dou lambda by dou t, such that all gauge transformations always preserve the Lorentz condition, that is this is always equal to 0, provided the original set of potentials they satisfy it initially, then such a kind of a transformation is a special case. It's known as a restricted gauge transformation. That is, transformations which take place between sets of potentials all of which satisfy the Lorentz condition. Then we say that those sets of potentials, they belong to the Lorentz gauge. So this brings me to the end of this particular lecture. So here there are 3 exercises that you can just try out. I'm not doing anything as an example here. You can just try it out for yourself. These are very straightforward. These 3 examples I have just picked up from Griffith's book. The first example, all you have to do is you have to check whether they in which gauges do they belong to, whether it's Coulomb gauge or Lorentz gauge. That's what you'll have to figure out. So how do you figure out? I'll just give a hint. In each of these 3 cases, what you have to do, your starting point will be, you'll have to find out the divergence of A. Just find out the divergence of A, because you see in this case, in all the 3 cases, phi is 0. Okay, phi is 0. So if the divergence is let's again go back to this condition, the Lorentz gauge. Okay, this is the Lorentz gauge condition. In all the 3 exercise problems, the phi was 0, right? So it means this right hand side will be 0. If it was Lorentz gauge, the right hand side will be 0. What you need to do is find out the divergence of A. If the divergence of A is also 0, then that means these exercises, they satisfy the Lorentz gauge. But if the divergence of A is not 0, then you have to further check whether the Coulomb gauge condition is satisfied or not. Okay, if the Coulomb gauge is also satisfied, Lorentz gauge, then you can just say that both the Lorentz and the Coulomb gauge, both of them are satisfied. And it is also possible that they need not satisfy any of these gauge conditions also. Just do this as an exercise. Just verify whether these 3, what are the which gauges do these 3 set of potentials do they belong to, or whether do they belong to any of these gauges or not. So these are the references. As usual, I've used John David Jackson and Griffith's book. I've mixed up the material from both these books. Thank you, and if you have any queries, please feel free to contact me. So this brings us to this lecture on gauge invariance. Thank you. I will be uploading these slides as usual on Google Classroom, and I will be uploading these 3 problems also on Google Classroom. Please do the problems and let me know if you face any difficulties. So, and stay home and stay safe. Thank you.